Well, was I just cheating? Did I just do that to make it come out right? And so notice as water's flowing up the plant, it goes from a diffusion pressure deficit, a suction pressure, so to speak, of near zero, about 0.1, to 4. Oh, no, that's the part in here. I'm reading the wrong column. 1 to 2 to 3 to 4 to 5 and then to 10. Okay, it's flowing downhill. The diffusion pressure deficit, the tendency of water to move in that direction, is increasing from 1 to 2 to 3 to 4 to 5 for different reasons. Sometimes it's osmotic pressure, sometimes it's turgor pressure. Why was the turgor pressure so low up here? And the answer is evaporation. So again, nothing special, it's just evaporation. When you have dry air, and that's something you have no shortage of around here, we have a whole different problem in Florida. And by the way, there are a lot of plants that can't grow in Florida because they can't move any water. You know, they can't do it. Okay, but up here, you know, this part's not going to be a hard problem, or in the desert or in San Diego. And so when you get to the leaf cells have lots of air spaces, and which root cells don't have. Of course, root cells are underground in a water-soaked environment. Here, the leaf cells are up here in the air with air spaces open to the air, encouraging evaporation. These little things are designed so they can open and close. They don't want to lose too much water. But they let the water evaporate, and so that lowers the turgor pressure. The osmotic pressure drew the water. The DPD, or xylem, as I mentioned, was about 4, just as normal osmotic pressure of mineral-rich water with no turgor pressure. But up here, the turgor pressure drops because the water evaporates, so the cell tends to shrink, and therefore it can absorb more water and still stretch. And so as long as you have dry air, I've got 10 here, but the diffusion pressure deficit of dry air in a desert on a warm day with a wind blowing can reach over 100. Okay, so now you're talking about an incredible amount of suction pressure drawing water up out of the soil. And of course, desert plants have all kinds of things to stop this so they don't lose too much water directly by evaporation. Redwoods, on the other hand, encourage this. And so as long as they've got continuous evaporation, and evaporation from a leaf gets a special name, transpiration. Excuse me. As long as water can evaporate from the leaf cells, that'll keep the turgor pressure down and the diffusion pressure deficit up, and the water moves all the way up to the plant. Now this, by the way, let me say this first. This is contrary to what a lot of people once thought, that a redwood is like a straw, you know, or plants like a straw. And so when you, suck water, or, here's an example. Okay, you have one of these things, and, you're used to, this is just water, by the way. Take my word for it. You think of yourself as, sucking water out of the glass, or Coke, or whatever. You aren't really doing that. What you're doing is sucking the air out of the straw, which creates a low pressure in the straw, and it's the outside air pressure that pushes the water up into the straw. How can you prove that? You get a really good seal. Okay, you can take a cup like this if you want, and put some Vaseline and some gum around it. Seal it so no air can get in, and what happens? You just try and try and try, and you'll get water up a little ways, but not very far. You have to have the outside air pressure. That's why, the cups always have a little vent in them or something like that in order to get that going. And so now suction pressure, so lowering air pressure, pulling the air out of a straw or out of a pipe, with a vacuum pump, can raise water about 30 feet if you had a really, really, really good vacuum pump. You could get water about 30 feet, and you can measure, pressure in terms of inches of water or in terms of millimeters of mercury. This would be a dangerous experiment, but you can use a shorter straw to demonstrate it. Instead of a 30-foot straw, if you had a little beaker of mercury, which I did as a kid. Nobody knew that it would give you, Mad Hatter Brother's disease and all that. And I probably would have done this if somebody had given me a straw. You know, you put a glass tube in there and try to suck up mercury. Well, of course, it weighs 13.6 times as much as water. You'd be lucky to get it up that far. The outside air pressure wouldn't push it very far. And same thing for plants. That you can't get very far. Under ideal, perfect conditions, you can only get water up about 30 feet. And so a lot of people have a mistaken notion that a redwood is a big suction pump. And it's just like a vacuum pump, pulling water out of the soil. Won't do it. A vacuum pump analogy will work for bushes this high, and that's pretty much it. And so the theory is called evapotranspiration. You have to have evaporation at the top. And what's going on here then is you're using a combination of osmotic, well, basically osmotic pressure, and reducing the turgor pressure, and that can reach much greater magnitudes of force than a regular vacuum pump can. And so there's the limits on this kind of pump. I mean, you could make one that could go much higher than a redwood. But it also requires something else. This only works if you're trying to move a fluid that's really sticky. Now, most of you don't think of water as sticky. You think of syrup as sticky. But chemically, water is very, very sticky. And so it has cohesion. Water molecules tend to stick together. Each water molecule looks like a little Mickey Mouse head. So the oxygen molecule is like that, and then the two hydrogens look like mouse ears. And there's 104.5 degrees between the two of them and so on. And the little mouse ear hydrogen atoms have a slightly positive charge, and the big oxygen has a slightly negative charge. And so they tend to attract each other, plus and minus charges. So water is very sticky or very cohesive. And of course you see that in a variety of ways. The skin, on the top of a pond, or a beaker or glass of water. Water forms a little skin, and certain kinds of water bugs, can scooter around on this little skin, or surface tension, of water. And of course, if you have